So we're going to take a look at a proof for the chain rule today. And this one's a little different than some of the other rules from calculus. The proof is definitely harder, a little bit deeper than trying to show the product rule or the quotient rule. So this kind of proof makes use of what we call an auxiliary function. And if you take complex analysis, or if you have taken it, this is a kind of proof that comes up a lot in complex analysis. And the idea is you've got some sort of tricky thing to show, and so you define a function that helps you show it. And these can look a little unsatisfactory because without any experience with them, it's not clear at all how one comes up with the auxiliary function that's going to help you. This will be, I guess, our first example of one of those proofs, and as you see more of them, probably not in here, but if you do any complex analysis, then you kind of get the hang of it a little bit more. So we're going to try to prove the chain rule, which is about the composition of functions. So the derivative of f of g at a point C is the derivative of the outside function f evaluated at the inside function g times the derivative of the inside function, so g prime of c. And we're going to show this by defining this auxiliary function d, which is going to look an awful lot like the definition for the derivative of f at g of c. But we're going to define d to be the difference quotient f of y minus f of g of c over y minus g of c whenever this is defined, right? And that means whenever y is not g of c. So if I plugged in g of c here, I would get 0. That's not okay. So we have to do this in a piecewise fashion. And if the denominator were to be 0, then we're going to define d to be f prime of g of c. Now, when we do that, what we've done is we've defined a continuous function, d. It's sort of clearly continuous. Be careful using that kind of language. It's continuous as long as y is not equal to g of c, because f and g are both differentiable, so f has got to be continuous, y is continuous. So continuity is not a problem unless we're looking at the sort of weird point where the denominator could be 0 in the top piece. But because of the way we define d of y, that point is actually fine too. If we take the limit as y approaches g of c of our auxiliary function, then by the definition of the derivative, that's equal to f prime of g of c, right? That's just taking the limit of this difference quotient on top. But then that limit is exactly how we define d of g of c, right? So the limit of d of y as y approaches g of c is the same as d of g of c, and so d is continuous. All right, so now we're going to take our definition of d, and I want to note that we can rewrite it this way when y is equal to g of x. Right, so the claim is that this actually holds for all x. So let's examine that for a moment. If we let y be g of x, then our definition is f of g of x minus f of g of c in the denominator, g of x minus g of c, in the numerator, g of x minus g of c in the denominator, and then if I multiplied both sides by the denominator, this is what I would get. Right, and then I would be left with the numerator on the right. And the only thing to check is that this still works even at the point where y is g of c. Well, if y is g of c, I get d of g of c here, g of c minus g of c, which gives me 0 on the left, and then f of g of c minus f of g of c is also 0 on the right. So this holds for all x, and because it holds for all x, I can work with both sides, dividing by x minus c. So d of g of x times g of x minus g of c over x minus c is equal to f of g of x is f of g of c over x minus c, as long as x is not c. So you might sort of see what's happening now. Just like in our proof of the quotient rule, I'm arranging for the derivatives I need to appear on both the left and the right. So when I take a limit on both sides, well, d of g of x approaches then d of g of c, and because we already showed the continuity of d there, I get exactly f prime of g of c. Right? So that's the definition of d of g of c. Right? It's f prime of g of c. And then the second piece is the definition of the derivative of g at c. And then on the right, that's the definition of the derivative of the composite f of g. Right? F of g of x minus f of g of c divided by x minus c, then you take the limit. Right? So here is the chain rule, and we're done. All right, now, again, that proof is a sort of more subtle proof than the ones we have been used to for derivative rules, and it's why you may not have seen an actual proof of the chain rule in calculus. I know if you had calculus with me, for example, we would have done something like the following. So the limit as x goes to c of f of g of x minus f of g of c over x minus c. And then we could write this as x approaches c, f of g of x minus f of g of c over g of x minus g of c times g of x minus g of c over x minus c. All right, so I've, again, kind of multiplied by a clever form of 1, rearrange things, and that makes it appear as though, as we take a limit, this one goes to f prime of g of c by definition, and this one goes to g prime of c by definition. And so this looks at first glance like it might be a proof, but we should be careful about this one. So if I present this in a class, I'll call it a plausibility argument. All right, so this gives you some intuitive notion that the chain rule ought to be true. But if we think about this for a minute, the difficulty with this seemingly simpler proof is in this denominator. Right, we can't have that be equal to 0. And unfortunately, there are functions for which this g of x minus g of c could be 0 infinitely often at points as close as you like, at points x as close as you like to c. So in general, there's no way to avoid that denominator hitting 0. And because of that, we have to do the sort of subtler proof using this auxiliary function.